Optimize. A Journey Through Database Query Optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
Yeah, right. So everyone should got notification that Project 1 has been posted. We did a quick update of the data set this morning. So if you just renamed a directory, it was a typo. And then I would try to cover Project 1 at the end of the next class on Wednesday, just a quick synopsis of like what's expected, what's involved. But the write-up should be pretty thorough and you should be able to get up and running fairly quickly. And you'll submit your assignment on Gradescope. And then if you haven't yet, please put your GitHub handle in that spreadsheet I posted on Piazza, and also put in your AWS account into that as well. And then we will then submit it to Amazon to get $100 for everyone to use for all your projects. Okay? Used to be to give you like $100 and it lasts like 2 years. I think if you don't use it, they take it away after like 6 months. They're getting smarter about it. All right. So any questions about Project 1 or anything about the synopsis? Anything else so far in the class? Okay. All right. So today we're going to be continuing our discussion on again the foundations and the beginnings of query optimizers, and in particular we're going to look at query optimized generators, sort of like these toolkits that are designed to be explicitly not a full database system, but something you could build and configure and tweak depending on for your target system, and then you can integrate it with whatever database system you're actually building. So before we do that, we're going to get through some corrections. Actually, well, first one's not so much a correction. I got this creepy email from somebody last week who says that they want me to move in with them because their marriage is falling apart, and somehow I'm going to figure that out. I don't know who the fuck this is. This is bizarre. We're not doing that. There was a real one, though. This is from somebody who pointed out that I had a typo in last class, in particular on this slide here, when we were showing the query graph model in Starburst, right? And I said Q1.price is less than or equal to all. It should be Q2.price, right? Because it's coming down from over here, right? So anyway, minor typo, but we'll fix that in the slides. But again, I've gotten some weird emails. That one, that's a new one. Okay. All right. So last class we were discussing Starburst, and in particular we were looking at this. Although this what is now known as a stratified search approach, even though the paper didn't refer to it as that, but the idea that there was going to be these two distinct phases in your query optimizer. The first was the rewriting, where you're transforming the query graph model to another query graph model. And the idea here is that you're applying transformations or rules to optimize the query where you don't need a cost model, where you know exactly this is something I'm going to want to do, right? And some of this was designed for, one of the big ideas was to get nested queries that maybe in separate query boxes, get them into the same query box as maybe like the root of the query graph model. So that way you can do a bunch of joins and not worry about doing a bunch of extra work on invoking nested queries over and over again for every tuple in the outer table, right? But again, the key thing about the rewriting was it was all just based on heuristics, right? And then that was the idea to get us into a query graph model form or representation that could then be gone through the plan enumeration process, where we would convert the QGM into these stars with these rules that can then convert the operators from one star operator to another star operator, or star operator to a lollipop, right? And they kept applying those rules and enumerating all the possible choices you could have in your query plan, and then eventually at some point you run out of time, or you've exhausted the search on everything, and then you end up with the final plan you can actually run. So the big thing we want to point out too as well, in addition to having these two phases, which we'll see in Volcano doesn't have this phase, and they call out the Starburst in particular and said that's not a good idea. We'll cover why. Then they introduced this idea that the properties now are going to be first-class components in the query plans and the rules, where the rules can be aware of whether or not a transformation is going to change the query plan in such a way that it would not be able to satisfy a property that's required by something above in the query plan. Like the sort order is the one that we keep seeing over and over again. If you know that the input of some operator requires the data to be sorted, as you're applying these rules in Starburst and you're transforming the data, if that violates that property or doesn't satisfy that property, then that's an invalid transformation and you don't do it. Right? Again, contrasting this with the earlier one in System R, it was keep track of the orders that I would care about, and then still run through the query optimization process, but not invalidate or throw away different choices because they didn't satisfy the sort property, and then go back later on and say, okay, well, if the best plan I've seen so far doesn't satisfy the sort property I need, if I tack on a sort at the end, what does that cost, and is that better than another plan that did maintain that property? Right. So now we're going to get rid of all those sort of hacks. Exodus will still do hacky, but Volcano will try to treat this again as a first-class property, or the properties of first-class components. All right, so we described this in the beginning of the semester, but we just bring up again because this is what everything is going to be today is going to be about. Is again this idea that the query optimizer is such a difficult piece of a database system to actually implement, the hardest thing you could possibly implement, that every time someone wants to make a new system, if they have to re-implement the query optimizer over and over again, then that's going to be, it sort of increases the barrier of entry to build a new database system. And the idea of an optimizer generator is that you abstract away the functionality of the optimizer, provide an API so that someone implementing a new database system could implement the necessary inputs to some optimizer generator, and then that thing will be run on the side as a separate service. Can integrate with your existing system, so you don't have to re-implement the wheel, right? We'll see. Let's see the two most famous standalone or modular query optimizers are going to be Calcite and Orca. They're technically not going to be optimizer generators as defined in the Volcano paper, right? Because that was all about you write these rules and we'll convert them to procedural code, and then we'll compile that for you, and then you link that into your database system. Those guys, you just implement their API in Java and that gets compiled. So whether or not that's the same or not, because you're not doing the transpilation, it doesn't matter. But the idea again, that you're going to have this separate thing that can generate an optimizer, an optimized optimizer for your database system, no matter what the data model is really key to what these guys are trying to do here. And a big part of that is going to be also then the separating with the transformation rules from the logical operators. And for the logical operators and the physical operators, like having these be sort of separate concepts in our system rather than try to intermingle everything all at once. We saw that a little bit in Starburst, the way they differentiated between stars and lollipops, and we'll see that again today with Exodus and Volcano, right? And then the idea again is that the mechanism we're going to use to figure out what rules we can apply to what operators, that's going to be independent from the search strategy. So that if someone wanted to replace whatever the branch-bound search you're implementing to figure out the best query plan, you could do that without having to rewrite everything. The first version of Exodus, we'll see in a second, didn't do that, and they had to throw it all away. All right, so we're going to talk about Exodus first, because a lot of the core ideas will be carried over into Volcano. But I love that Volcano paper you guys read because they talk about all the mistakes they made in their own previous system, as well as comparing and contrasting with another system like IBM. So and to me that of all the papers that this guy Gertz Graffi has written on his 3 query optimizers, Exodus, Volcano, and Cascades, the best one that he wrote is the Volcano one. Because again, it's like the System R one. You could take that and actually re-implement, maybe not all of it, like a lot of it. All right, so I sort of said it before, just now, Gertz Graffi is a very famous database researcher. He's worked on 3 query optimizers in the 1980s and 1990s. And so he really pushed this idea of an optimizer generator for almost a decade, or over a decade. And he sort of, again, laid the foundation for how we want to build these systems today. So the Exodus optimizer was part of this larger system that was being built at the University of Wisconsin called Exodus. And similar to what Starburst was at IBM, it was meant to be this extensible database system project, right? Because that was the hot thing, as I said, in the 1980s, in response to the object-oriented databases that were coming out around the time that were trying to say, you want to do more complex things in your application code than you could do in the relational model. Therefore, you need an object-oriented database. And so all of these toolkits and these extensible systems were really meant to show, oh no, you can actually do all the things you would want to do on objects inside of a relational database system. And a big part of that, and again, is having to provide a query optimizer that you could extend, right? All right, and for those who don't know, Wisconsin is usually one of the premier database universities in the world. That guy, David DeWitt, was Jignesh's PhD advisor. Obviously, he was Graphi's PhD advisor. He's like, probably the second famous database researcher in the world, after like Stonebraker. If you say that DeWitt, he'll get mad, but he hasn't won the Turing Award. All right, so again, what Exodus is going to do, again, have this idea that you're going to separate the logic we're going to implement in our query optimizer to do the transformations from a logical plan that's coming out of our parser and binder, and then produce a physical execution plan that we actually can run. We're going to keep those things separate, as well as the data structures we're going to use on the inside to maintain all these things, right? And we're going to avoid exhaustive search in the way that System R was doing, not by throwing away plans that we maybe don't want to look at, like bushy join trees, but by using sort of dynamic approach and a branch-bound pruning to identify, have we seen this path in a tree before? Although Exodus is not going to do a good job at that. Volcano will do better. And if I traverse down a tree, is it never going to be better than the best query plan I've seen so far? And you try to avoid those unnecessary computations. One of the cool things that Exodus is going to do that Volcano isn't going to do, Cascades doesn't do, but we'll see later in the semester, and I'll show you what Exodus does, is that they're going to try to learn the ordering of how to apply the rules and the effect that a rule may have on the cost model from past experiences. Meaning, like, if I run the query optimizer for this one query, and if I see it makes certain changes that are, for certain rules, probably certain changes that are beneficial more quickly or early in, or like, if I see rule transformations that are beneficial to my query plan, I'll try to prioritize them the next time I run the query optimizer, because they might, I might be learning that those things are going to be a good idea or not. Yes?
So are they learning in the sense, like, are we already putting that you learn this, like, you put it as like a rule or anything? Or is it learning automatically via like the stats or like?
His question is like, how are they doing this? We'll see in a second. But you're basically asking, is it a rule that you would have that say, go learn this? No. This is like, it's the search strategies, the thing they're going to have on the inside that you don't have to modify in the query plan. It's not additional rules, right? It's like the idea that you have a cost function to say, here's the cost of executing this query operator, this physical operator. I can learn how much better that's actually going to make me. It's all done in the query optimization, so it's actually not going to be, when I actually ran it, did it actually make a difference? We'll see that later in the semester where they do try to go learn. I tried this rule in the query plan and during the optimizer, and I got this benefit, this expected benefit. When I ran it for real, did I actually get that benefit, yes or no? And you have a feedback loop to say, is this good or not? This is just like on the inside in the system itself, sort of think of a closed system. So you're not actually running the query. You're just saying, if I apply this transformation according to my objective function, my cost model, am I going to get a benefit of that? If yes, try to do more quickly in the future. Okay, and then just like in Starburst and in System R, they're going to do a bottom-up approach. Another way to frame this is also forward chaining, because it was the 80s. But we'll explain the differentiation between forward chaining and backward chaining between Volcano and Exodus later on. All right, so I'm actually glad you're here. The initial implementation of the first query optimizer they were built part of Exodus, they knew they were going to do rules, and because it was the 80s and people were being experimental, they thought they would just use a esoteric programming language that was based on logic programming from as again the first class concept that they're promoting, and just define all the rules in that programming language, which then would have its own runtime that can do the pattern matching and instantiation of the rules and the application of them and expansion of the different sort of facts, if you will, in the query plan automatically. So they like, all right, well, it's the 80s, let's do this. So they pick Prolog, but then they talk about how they end up throwing it all away and rewriting everything in C because they found that the language's runtime has its own built-in search algorithm doing depth first search. You can't really change that and manipulate its behavior at runtime based on the results of the rules that as you're applying them. You sort of like, you told Prolog, like, here's all the rules that I have. Things aren't going to get changed. Just go, right? And then furthermore, I think they had their own implementation of the Prolog interpreter. Again, it's the 80s, before the internet, where there was widely available ones. And that thing was just too slow for them. So they threw this first implementation away and switched to C. So what's the lesson here?
Don't use esoteric languages?
Don't use esoteric languages. What's that?
Don't invent your own.
Well, they didn't invent their own language. Prolog and loop are things that existed before.
They write their own interpreter.
Oh, well, I mean, yeah, as systems people, that's okay, right? I would think that, so I would argue that like you could, I supposedly take that language, the Prolog, and you could then recompile it into something useful like C, right? But they just didn't do that. They switched everything to C. They actually invented their own programming language for the actual implementation of the system called E, which I think was based on, I think it's based on C. I think loop, where did loop come from? Loops, was this Dennis Ritchie? I'm looking at you, sorry.
I have no idea.
One of these, I think loop might have been implemented by Dennis Ritchie, the guy that invented C, or they based what they were doing on E based on Dennis Ritchie's early language or something. Whatever. Like they did in Prolog was a bad idea. Again, it was the 80s. People were doing a bunch of experimental stuff, right? Does anybody know what the first programming language Postgres was written in? I've said it before in classes. What is Postgres written in now? C. What was it written first?
Basic?
No, basic.
I don't know, I guess.
Think the 80s. That's the 60s. That's early 80s, yeah. Lisp, right? So then what do they have to do? They had to write their own converter, the transpiler, to convert the Lisp into C, and then actually compile that, and actually, because you need a runnable system, right? But in the 80s, when people were doing wild stuff, they were trying to like build CPUs that could just run Lisp directly on the hardware. Like people were trying all sorts of weird stuff, especially in Berkeley. So that was a mistake. They ripped all that Lisp stuff out and rewrote everything in C. And that's what the code base we have today, right? Anyway, I'm not here to bag on Prolog. There is Datalog, which we're not going to cover in this class. That's a more useful version of Prolog for databases, but most people don't write that kind of stuff. All right, so here's what the pipeline is going to look like. So you have this database system implementer, the person that's trying to integrate the Exodus query optimizer or Volcano's query optimizer in their system. So in the case of Exodus, they have to provide a model description file and then C functions that implement the different operators that you're telling the optimizer that your system is going to support, right? I think there comes obviously some built-in ones like scans and joins and so forth. But if you wanted something beyond what the sort of basic relational algebra constructs that they had or operators that they had, you would provide those as well. And then you feed this into the optimizer generator, who's going to then crunch on that, spit out a bunch of C code, which then just invokes GCC or whatever your favorite compiler and linker is. You produces a shared object file that you then would link into your database system. Right, so they would call this sort of the database system generation time. So this would be done as part of the compilation process of building the actual software of the database system. And then when it's actually deployed, the SQL query shows up. We run through the parser and the binder just as we did before. This produces a logical plan, which we then feed into the query optimizer, does all the stuff that we're going to talk about now, and then it spits out a physical plan. Right? So again, the idea is that instead of writing a query optimizer from scratch and having it deeply ingrained or embedded in the database system, it's a standalone shared object that you then link in. It provides you the function, and then that avoids every single data system have to re-implement their own query optimizer, which, even though this was written in 1987, it's still pretty much true today, right? So this would be the query execution time. Calcite and Orca will see attempts to try to provide something like this, but people are. There's very few systems that are using Calcite in its entirety, and the people using Orca are pretty much people writing Orca. So it's not really widely adopted. Okay, so what's in this model description file? So we have the operator definitions. You have to tell it here's the number of arguments, here's the name of the operator that I'm doing, and any additional properties or expectations I would have that are required for that operator to process data. Then you have the access method definitions, like what kind of indexes are available, is the data coming out sorted or not. Then you have rules for transforming the query plans, and then additional rules for mapping which operators can access which of the access methods that are defined above. So this is just metadata telling the optimizer in a structured form of what the C code you've implemented that you're providing it, what arguments they're going to require, what their data types are, and so forth. Right? Think of like this is like before annotations in Python or whatever, Java, whatever your programming language is. And then now we want to talk about what the rules are going to provide. So they make it explicit differentiate between transformation rules and implementation rules. And you can sort of think of this as, again, like in the context of Starburst, there was stars are really were really sort of a higher level class of an operator doing some sort of higher level function. But then there would be a rule that could then convert that star into another star, or star into a lollipop and a bunch of other stars. But they just always sort of called them rules or transformation rules. In Exodus and Volcano, they're going to make a distinction between the transformation rules and the implementation rules. I should also say the paper can be quite confusing sometimes. And the textbook for the next chapter we'll read on Wednesday in Cascades, it'll clean up that up a little bit. Part of the reason I'm not having you guys read the original Cascades paper is because they refer to, I'm going to do a transformation, but that transformation will be based on an implementation rule, and then there'll be expressions, we'll cover in a second. Like they're running. It's hard to say. The number of terms that they have that get overloaded for what they're trying to do in the context of a query optimizer can get quite confusing. So again, even though if you read the paper, it'll say, when we apply this implementation rule, it does a transformation. That's different than what they mean by a transformation rule. All right, so transformation rule is going to be a way to map a logical operator to another logical operator. And then they'll have additional hints in the definition of the transformation that would show up in the model description file that can give warnings about whether this thing could get stuck in an infinite loop. And this exclamation points are trying to say that if I do this commutativity, changing the join order of AB to BA, I don't want to then apply the same rule to go back from BA to AB. So they just have a little flag here that says, okay, when you apply this rule, don't try to apply it again on the output that you just generated. And then the implementation rules, again, are just mapping from one or more logical operators to one or more physical operators. And so this is going to be a key distinction in Exodus compared to Volcano. This is more aligned with sort of what Starburst is doing. So I think Starburst is more convoluted than this in some ways. But what they're saying here is that in Exodus, they would actually recommend that engineers, or the people actually building the systems, the implementers, that they would manually combine rules if you knew that they were always going to be sort of executed in sort of successive order. Like if you're always going to know you're going to move a filter below a join and then do some other transformation right after that, because that's the plan that you want, they would say, well, don't implement them as separate rules. Combine them together in your code so that they're a single rule. And that way, the search process is more efficient because it's not spending time applying the rule, then looking up in the table to see what's the next rule apply, and then go ahead and applying it again. Volcano's not going to do that. Volcano's going to say it's better to learn that these things should be composed together one after another, and not try to combine them, because that just increases the complexity of the implementation. It makes it harder to reason about the changes that you're making in the optimizer. So again, Starburst sort of claimed they wanted this too. They wanted all the rules to be independent, but it's a little more complicated than what Volcano is going to do. The other thing they're going to also be able to do is support bidirectional rules, meaning you could have a sort of a logical to physical transformation, and then also go back in the other direction potentially, and go back from physical to logical. Volcano's not going to do that. right? All right, so the search algorithm is pretty straightforward in Exodus. And the way they're going to figure out what's the next rule to apply, and this is basically re-implementing the sort of the runtime that would be in Prolog to figure out what's the next rule to apply. They're just going to maintain this priority queue called open. It has some term from AI from the 1980s, and that's what's referred to that. But they have this priority queue called open, where that's just going to have all the transformations that it can apply next. And this is just going to be a list of references to the transformations that are going to live in this thing called the mesh. And it's just an in-memory hash table that's keeping track of all the transformations that it's applied. It's going to keep track of all the logical and physical operators that they're going to have already performed. And then the transformation rules are basically doing references to those operators. And then the system basically looks up in the mesh, finds that those references, and then does the transformation. Or if they don't exist, then they go ahead and apply them. Right, so it's a really simple look. While there's more transformations to perform, you select the first one from the queue, apply all the transformation rules based on for the things that exist in the mesh, and then you do the transformation rules. Then you do the implementation rules to convert all the logical operators that you've generated from the second step here. Now you're going to immediately convert them to physical operators and do the cost analysis to figure out which one is actually the best one to pursue. So they're going to be eagerly going to consider and evaluate all the physical operators immediately after doing a logical transformation. Volcano is going to do a little bit of that as well. Cascades is not going to do that. Cascades is going to eagerly apply the transformation of converting things to physical operators as it does the traversal, and not rather than blowing up the search space right away. So the key thing they're going to do, though, that's actually kind of interesting as well, is that they're going to, at the beginning of each round, they're going to take a transformation rule, and they're going to try to estimate what is the improvement I'm going to get upon doing this transformation, and then they're going to prioritize them based on which one is going to have, you think is going to have the biggest win, and they call this the expected cost factor, right? So the open already is a priority queue where there's something else that's keeping track of the priorities as you want to apply them, right? And then as I do the transformations, I want to be able to look at them and figure out, okay, the ordering of the priority queue is going to be based on this expected cost factor that's going to say, here's the thing I think is going to make the biggest benefit or provide the biggest benefit to the overall cost of this query plan. Go ahead and apply that first. So the way to sort of think of this is like, if my total cost of my query plan right now is some value C, then the expected cost of a transformation is going to be this F that's going to say, here's the effect of applying this transformation to my query plan and how that's going to affect the cost. So the idea is that if this F is less than 1, then you know it's going to, or you think it's going to have a bigger benefit for you. And the closer it is to 0, the better, right? For neutral rules, like joint commutativity isn't necessarily one, but like I'm trying to think what would be a neutral rule here. Like maybe projections don't matter that much in your database system, and you did a projection push down, right? You could have, that would be considered like a neutral rule. So rather than just going to the cost model always and say, okay, what's the benefit I'm going to get for this transformation? They're going to try to learn what that benefit's going to be and apply this, what they call a propagation adjustment. And the idea here is, again, I want to keep track of the last n number of times I've applied this transformation rule and what benefit did I actually get from it. And they have a bunch of different formulas, like different ways you could calculate this, right? Where one could be just take the sliding average across the last k number of transformations or attempts or times you apply this transformation, right? It could just be all of them, but that now you start keeping track of the history of everything. That becomes, in the 1980s, that become very expensive, right? They basically say it doesn't really make that big of a difference, but they thought this was a good idea, that you want to keep track and learn when I apply this transformation, how much benefit did I actually get in the future? And that can guide whether it makes sense to apply the same thing again. They don't go into details how they consider things like, what if the data changes and how do you invalidate this, right? What if the parameters for a query, what if that changes? How do you account for that, right? I mean, certainly you can imagine for a single query, if that's the only scope that you're looking at as you apply these transformations, then that's the things that I said aren't a problem anymore, right? Because it's like I'm applying this one query, I'm applying this transformation all over again. How much benefit did I actually get? But when you do this across multiple queries over longer periods of time, this becomes problematic. Yes.
How does it, like, what does it compare to? Or
What do you mean?
when you mean like the real cost versus what was expected?
So the question is, in the context of this, yeah. So again, we're not talking about like actually running the query. They're not doing that. They're just trying to say it's an expectation of what I think the benefit's going to be, but at this point, I only have a bunch of logical operators. So I think if I convert you to a hash join, then I'm going to get this benefit. So I sort of estimate what that boost is going to be. Then when I actually do it, then I run my real cost model. That'll tell me how much benefit I do get. So this is like an approximation of its cost, because again, logical operators don't have costs. And as far as I can tell, again, they scope it to make this work. They scope it within the context of a single query, but you can imagine that you would extend this across multiple queries. And as I was saying before, this is just within the query optimizer itself. There's nothing about whether I apply this change did actually make the query run faster, right? Because that's actually really hard to do, because what if I apply some change, I get some benefit, but then my final query actually doesn't even include that change. Now I can't actually run the query and get any feedback for this, right? The other thing they also talk about is when they apply a change, and you get sort of this propagation adjustment, you don't actually apply it to whatever the transformation rule you just applied. You apply it to that one and the previous one. Because it may be the case that there are some transformations where the first thing you apply makes things actually worse, but then that sets you up in such a way that then you apply the second one, and now you break out of, you're out of the valley in your search, and now things are much better. So they hard code it so that the propagation adjustment is applied to the last two. Should it be 3? Should it be 4? I don't know. They don't say, right? This seems kind of hackish. Like it's in the right spirit, but I don't think this is the right way to approach this. But it's good, again, they're thinking about this idea of like, oh, can I learn from past experiences in the 1980s? Whereas now that's sort of taken for granted with reinforcement learning, AI, and other things. All right, so one of the big flaws that Exodus is going to have is that the way they're going to represent all the operators that I currently have, that I've generated through these transformation rules in this mesh hash table, the way they're going to organize that is the entry or the key that you're going to do a lookup on is going to be a combination of the logical operator and then the physical operator it got converted to through an implementation rule. So that means if I have a logical operator that can get converted to a sort merge join, and the same logical operator can get converted to a hash join, I'm going to have two different entries in my mesh hash table representing both of them. Right, is that clear? Right, because Volcano is going to do something different. Cascade is going to certainly do much different as well. Right, so that means basically now you have you have all these duplicate logical operators in this mesh hash table because they can't sort of have a linkage from one logical operator produces multiple physical operators. All of the additional logic that you're going to have about having, when you add additional operators that can then require certain properties, that logic has to be put into the cost function. Right? So you could have this notion that like an operator expects this data to be coming in a certain way, but then if you want to push the query plan to make sure that those things get satisfied or enforced, then that logic's got to exist in the cost model itself. And as I said, as soon as Exodus applies a logical transformation rule, it then immediately applies all the implementation rules and basically explodes out the search space. even though some of these transformations you do in the implementation rule may not actually be a good idea or not. Right? There's other things that they talk about in I think it's in the Volcano or maybe it's either the Volcano or the Exodus paper, where they talked about how because it was the 80s again, they wanted to use the A-star search algorithm, if you're familiar with that, but they were not able to calculate the expected benefit, the promise of the improvement you're going to get from the implementation rule in such a way that the A-star algorithm needed, right? Because you can't have like things oscillate back and forth, right? It has to be a clean step function, right? All right, so then that takes us now into Volcano. So Gertz Graffi graduated from Wisconsin, and then I think he was a professor at University of Colorado, and then he became a professor at Portland State. I don't know the details of what happened there. But again, he was really pushing this idea of optimized generators for several years, and it's really groundbreaking work. So the Volcano project was similar to Exodus, where it was meant to be this again extensible database system toolkit. When we discuss the exchange operators and parallel algorithms in the intro class, right, we sometimes refer to that being like the Volcano method, right? That all comes from the same project that he built for this query optimizer as well. So again, just like in Exodus, it was meant to be a extensible system where you can add new operations and equivalence rules for them, right? Once again, we're going to try to treat first-class properties. Treat properties on the data as first-class entities during the planning process. They'll do a little bit better than Exodus, but Cascades, we'll see on next class, does it correctly. Handles all corner cases. They're also going to do that same rule compilation pipeline we saw in Exodus, where you define these rules in a higher level with higher level metadata. You then provide also C implementations for the different operations you're trying to add or operators trying to add. And then they'll compile that for you into a shared object that you then linked into your database system. So, but what's going to be different, what they're going to do is then Exodus and Starburst is now this can be the first example of doing a top-down search to generate the query plan or backward chaining, based on a branch mountain search. And the big thing that now they're also going to try to do that Exodus couldn't do is that they want to be able to generate all these different permutations or apply the rules and start applying changes. And then not have to go repeat and revisit things over and over again, right? Because the way that the data structure that was being maintained in Exodus wasn't allow them to keep track of things. So this was never, the original source code was never used outside of academia. I think Exodus was used for a prototype object-oriented database system out of Texas Instruments in the 1990s. But I think beyond that, I don't think it went anywhere. And then this is what CalSite is supposedly, at least what they claim that they're based upon in their implementation in their paper. All right, so it's interesting to look at what are they going to try to actually achieve in Volcano that Exodus couldn't do, right? And I will say also too, like if you ever heard the term second system syndrome, right? This comes from IBM. Basically, the second system syndrome is like if you build say you're on a project to build one new system, and you say, okay, let's build the next one, to do a rewrite. So when you build your second system, you're trying to correct all the things that you did wrong in the first system. But then you say, well, if I'm already rewriting the system, let me go add this feature and that feature, and let's do this crazy thing, right? You start adding a bunch of new things in the second system, and then the second system never ends up getting built, right? And so I have to give him credit, like Volcano is his second system, and he got it done. He followed his goals, and he actually implemented reasonably well. All right, so just like before, they want to interoperate with existing database systems. They want to be more computational and storage efficient than Exodus was, so you cannot have this mesh table explode with all the possible things that you've ever seen before, or having to generate things ahead of time. They want to have extensible physical properties beyond just sorting and compression. Right? You want to be able to specify these things more easily and support them as, again, first-class properties. They want to be able to allow you to rewrite the search and the ability to figure out how to prune the branches as you're doing the traversal. That one I don't think ever, right? I don't think they ever went beyond the depth first search algorithm that they implemented. The paper talks about it'd be nice if we can do this in the future. And then we're not going to talk about this too much right now because we'll cover this later in the semester. But they want to have the cost model be able to support what are called parameterized queries, where they are query plans where you may not actually have all the constants for the values that are being used in predicates or like where clauses. Select star from table where ID equals 1, 2, 3. Well, if you declare that as a prepared statement, you would say select star from table where ID equals question mark or $1. And the idea is that at runtime, when the application actually invokes that query, they would invoke it as a prepared statement and then pass in the value to that parameter. And so ideally, you want to be able to generate a query plan as soon as you're told, hey, prepare the statement, and then at runtime later on, go then fill in that value, not to maybe run through the whole optimizer again. Again, the paper doesn't talk about too much about how to support this. It's actually becomes really challenging if you have, if you try to accommodate, if the query plan's structure can change a lot depending on what those values are being passed in as the parameters. And so again, we'll spend a whole day discussing how to handle that. But that's another big challenge. I think they had basic ability to keep placeholders in, and you implement your cost model to say, hey, I don't know what this value is, so let me just pick the worst one or the average. And that's all they were doing. All right, so in the implementation itself, they're now going to be introducing this logic, this idea that they have two distinct algebras, one for the logical expressions and the physical expressions. And this is going back to what I was saying before, where they're overloading a bunch of terms to mean very explicit things in this paper. Cascades will go even worse. But they're basically introducing, they start throwing around the term expressions. They're like, okay, well, they didn't define it. What does that actually mean? I'll show this in the next slide. It's basically those query boxes we saw in star versus QGM, the query graph model. It's just saying that some complete sort of select operation with the from clause and so forth. All the rules are going to be independent. And then unlike in Exodus where they said, oh, if you know these rules should be applied one after another, combine them together in your implementation. In Volcano, they're going to suggest or advise you not to do that and let the query optimizer or the search engine figure out on its own that these rules should be applied one after another, rather than you having to manually enforce that. You could still do it, at least I think you could, or maybe the pattern matching doesn't support that. But it's better to have the optimizer learn this for automatically, because again, any assumptions you make about the data at the time you said let's combine these two rules together, that might get broken or not be true in the future. So if you just have these be small atomic units of rules, and we'll put things together. They also discussed that they had this internal debate about whether they should even continue with Exodus' approach of let me compile everything in sort of the setup or the system generation time. Let me compile all my rules into C code and then to machine code, because that's going to run for a faster search, as opposed to using an interpreter, which is what Starburst started off doing, so that you could dynamically change the behavior of the query optimizer while it was running without having to recompile and link everything back in. And so that flexibility is nice. I think at the time they said the only one that was doing this, at least for the Exodus paper at the time, the only one that was doing that, the one that was doing this was Starburst, and Starburst was doing interpretation. So in this Volcano paper, they say, okay, well, now that you see Starburst, they're doing interpretation, and we did Exodus at compilation, we think it's better to have faster search, so they're going to stick with the compilation approach. In Postgres, you can install new rules, but because you just insert into the catalog table, like PG rules or something like that, and this system knows how to do lookups at runtime. But they're not trying to do full query optimization the way that Volcano is doing. All right, so what is an expression? Again, it's a term that they're using to define some scoped query that you're trying to reason about in your query optimizer, right? So in the case of a logical expression, it's just saying that's a representation of the query that the user is requested, defined as logical operators, and then the dependencies between them. And the physical operator is just the same thing. It's the representation of the query plan, but through physical operators that, again, you could take this query plan and actually run it in your database system, right? Assuming that it knew how to read them. So the key thing also to point out too is that in all these early query optimizers, they're all assuming they're operating on trees. We'll see later on from the Germans that you actually want to use DAGs, right? Direct acyclic graphs, and where you may want to have an operator have two parents, whereas in all these tree structures, it's always going to be one parent. And the reason why I want to do this is because if you want to start materializing intermediate results through like a CTE or a nested query, you may have different parts of the query plan when need to feed that data into it, right? Now you can cheat like Postgres does, and you basically have a reference to say, I know my input is this subquery that's defined in another part of the query plan, right? But when it comes time to doing more complex transformations that they're not doing here, but we'll see later on from the Germans, that you want to have things represented as a DAG. That's just an aside for now. All right, so this should not be. This is all going to start sounding the same from what we saw before, where you have these logical operators and they have these different properties, the schema, the cardinality, and there's a property function to say, is this thing providing this property or not? For physical operators, same thing. They have their own kind of properties. They want to have a cost function because now you can say, here's the expected cost if I run this physical operator in my query plan. Whereas again, in logical operators, there is no cost. Like how much does it cost to do a scan? Well, it depends whether I'm doing sequential scan or index, right? So you can't do that there. And then there's going to be this notion of this applicability function that's going to say, is this physical operator going to provide or satisfy the physical operators that are defined from the logical operator that it came from? And then now they're going to introduce also these enforcer operators, which are like these virtual or stand-in operators that don't really map to anything that we'd actually execute. It's just a way to have a sort of a barrier in our query plan that says we need to have the data being fed up through this part of the query tree provide the certain properties that we care about, like sort order. So again, the enforcers, they're just the same thing as they're basically equivalent to the glue operators that were in Starburst. It's just a way to again keep track of in my query plan as I'm examining it. Is the data coming up through the stream or the edge in that tree? Is that going to be in the form that I need? Right. And then so if you're integrating Volcano with your database system, you have to provide again. Here's what my enforcers are, and here's the properties that they're going to be handle. I think they can. If you just say I need an enforcer that can guarantee these properties, they'll then synthesize that code for you. Right. So it's not like because the enforcer is not really doing anything. Right. It's not taking any data. It's just there as a stand-in to say I need data to look in this form. So the rules in Volcano are basically the same thing as in Exodus, right? You just have some matching function that then that looks at the form of the query plan. If it matches the matching function, then it then fires off an action function to go ahead and do the transformation, right? And then to avoid having to have for all possible combinations of logical plans or physical plans. You can parameterize what these matching functions to say, like, I have a join, right? I'm doing a hash join, and then below me could be a scan operator. I don't care whether it's index scan or sequential scan, right? You don't have to define for all possible combinations, different rules for these things. They have this thing called auxiliary functions or support functions. And my understanding of those, these are just, if there's additional checks you want to do after the basic pattern matching is done on the form or the structure of the query plan. Like if you want to examine more information about what's inside of the operator itself, then you can tack on these support functions that then just get fired after you pattern matching. So the pattern matching is supposed to be done in this high level dialect. Well, I don't think the paper doesn't say, right, in this DSL. But if there's things you actually want to explicitly check through procedural code, you then provide this additional function. The cost functions are also abstracted away in the implementation as well. Again, this is something that you as the data system implementer has to provide. And to think of like, again, in an object-oriented model, you would have an abstract class of a cost, and then you have to, if you overload it or you override it, you have to provide like the plus operator or the equals operator, less than, greater than, and so forth, right? So there isn't any notion built in of what the cost actually is. It's not based on CPU or anything else that Volcano is aware of. This is what you have to provide. And again, it doesn't use that expected cost factor or the propagation adjustment that we saw in Exodus. They completely abandoned that. I don't think the paper even mentions it. All right, so what is the search algorithm? So again, the setup of the rules looks basically the same. The properties are a little bit more nuanced than in Exodus. And again, now we have these explicit enforcer operators that can guarantee that data is going to come up in the form that we want. So the search I'm going to use is a top-down approach that's doing backward chaining. And the way to think about this is it's a goal-oriented search, meaning I'm going to start with the answer that I want to have, meaning what's the final result of the query itself. And then I'm going to traverse down and start filling in the physical operators that will get me to that point. And just like before in Exodus, where they had this hash table to keep track of, here's the things here's the operators that I've generated as I apply these rules, they're going to have the same thing. They don't give it an explicit name. I think somewhere in the paper they call it a lookup table. In the Cascades work, you'll see this referred to as the memo table, but it's basically applying the same idea. But the memo table in Cascades is more sophisticated than this one. So now, as I'm sort of each round of my search algorithm, as I at some point in the query plan in the tree, I have say examining a logical operator. I go look to see if I apply a transformation, does that outcome of that transformation does that already exist in my lookup table? If yes, then I don't have to reapply it. If no, then I do apply it and then I fill it in. So the next time if I try to apply it again, I'm not burning cycles doing the same thing over and over again. And this is going to allow us to be able to reuse the cost calculations we've generated and within the context of a single query, because the data is not evolving, it's not over long periods of time, that we can reuse any calculations we already produced and not reanalyze different subtrees going down. Whereas Exodus could not do that. So again, top down versus bottom up or forward chaining versus backward chaining, right? At a high level, the two terms are basically the same. But just for clarification, backward chaining is basically say you're going to start with at the roots. It's really defined in terms of like logic. We see here's the facts that I have, right? That I'm going to scan a table artist. I'm going to scan a table appears, and then I can apply then the rules to say for that for these base operations or base access methods. Here's the rules I can apply to generate different choices. And then each level I figure out which one's the best one, keep those around, and then I traverse up and look at all the next rules and so forth until I end up my goal at the top. Right? We saw this before in System R. In the backward chaining, the idea is, again, you start at the root. I want my answer to be the output of a query that has artists joined with appears. So I first go down to one level below and say at the very beginning, I just have one choice. Like I knew a transformation from this logical operator. I can produce one physical operator. And then within that branch of that physical operator, I can get down to say, okay, what's the best way to access artist? Go down the other side, get the best way to access appears. And now at this point, then I have a complete query plan that I can actually execute. And there's a bunch of things I may not even have had to consider. Right? I can get to I can get to an initial query plan more quickly than I can if I'm doing the forward chaining. It may not be better, but I can certainly get to a initial plan more quickly. Yes?
Is the goal to have like an initial plan ready, or is it like to have how does it adjust itself to have a better result than before?
So his question is the goal to have a plan more quickly? Not necessarily. Depends, right? If the query is so simple, you might be able to find it more quickly. But then, this thing's going to rip through it too as well, right? The thing about Volcano is that it's, again, contrasting with Exodus, it's only going to explore the subqueries for any, for part of the plan that actually can contribute to the expression. So like if it could decide, again, this is where I know what Cascades is, I know what Volcano is, and the lines get kind of blurry. So I might be saying something that actually is in Cascades and not in this one, but bear with me. The idea would be, I look at my choices as I'm exploring down, I can set priorities for them and say, this choice is probably gonna be better. Let me just go examine this and don't even bother looking at the other one, right? It's sort of like the expected cost adjustment or the prioritization adjustment we saw in Exodus. That's right, I think this is actually in Cascades, not this one.
This is Cascades.
What I'm describing is Cascades, yeah. So ignore what I said, next class, right? So in this case here, they would actually, in Volcano, they would have to explore all of this.
There is no guidance in Volcano.
Yeah, there's no guidance in Volcano, thank you, yes. There's 3 of them, it's hard to keep track. Okay. All right, so let's look at this example of Volcano. Thank you. All right, so again, we started at the very beginning. So it's that query we had before. We want to get all the artists that appear on Mushu's tribute album, and then we want to order them by the artist ID. Right. So the little red piece here, that's the property we need to enforce. Right. So starting at this point here, we want to then apply the different rules that are available to us to then fan down the search tree to start filling in the pieces that we actually need. So a simple transformation could also be as well, although this would be coming out of the logical query blend. We know we need to order the first 2 tables in some way, and then we want to order all 3 tables together. Again, because it's PowerPoint, I'm not showing all possible combinations. But you can imagine for all different orderings of the logical orderings of the joins would appear here as well, or the physical ones as well. So I start at the very top and say, okay, well, I want to produce something below me, a physical operator that's going to give me the output that I need of artist joins appears, joins album, and that output has to be sorted by the artist ID. So I would apply all apply the logical physical transformation that would convert that 3-way join into a join implementation. Right? I get either a hash join on A1 on join result A1 A2, do a sort merge join on the join result A1 A2 with A3, or I can introduce an enforcer operator that just says, well, I don't know how you're going to join this still, but I'm going to guarantee whatever data is going to come out of me is going to be sorted on the thing you want it to be sorted on. All right, so say then we can then do a, we could throw away this hash join. Actually, you wouldn't actually even generate the physical operator for this because it would violate the sort order here. So yeah, maybe I just wanted to show that existed, but you wouldn't actually even expand this out because it would say this doesn't provide the data in the sorted order that I need, so don't even bother doing it, right? So that, we just ignore the hash join. But at this point here, I'm cheating and say instead of a merge join, it's a sort merge join. So the sort is built into the join operator. But that's going to guarantee my output. And then this enforcer, I don't know what is actually below it, but I know it's going to guarantee my data is actually sorted. Yes?
So is the artist ID lies within the A1 and A?
What? So this artist ID,
Yes.
like this thing up here?
Yeah.
What is that? So I don't have the SQL query here, but I showed it last class. It's a select query with order by clause as artist.id. So again, this is done in PowerPoint, but the binder would know that you're referencing some column, right? And be able to map that to whatever, I have A1, A2, A3, it's just artist album appears or whatever, or as it appears at the top, that I know that I want my data to be sorted on one of the tables that's feeding up into me on one of their columns.
There are a lot more rules, right? This is incomplete.
This is very incomplete. This is PowerPoint. Yeah. It's PowerPoint and animations. They're not. Yes. There's way more rules. Yes.
So is the right-hand side means we join all the table and sort it, or we sorted the artist table first and then join?
Your question is what? Sorry.
So the right-hand side on the last
Like
one.
this one here.
So that means we join all the table and sort it, or we sorted the artist table, and then join it. Is that?
Yeah. So maybe it should be a different color, maybe red or something. It's not a physical operator because it's not actually doing anything. It's a placeholder to say, I don't know how I'm going to get the data below me at this point as I'm traversing down the tree, but I guarantee it will be sorted. That's all it's saying. So,
sorry, go ahead.
No, go ahead.
So right now it's still like any logical phase.
Say it again.
So right now it's still in the logical phase.
It's not a physical operator. It's not a logical operator. Again, think of it. It's red, right? It's just saying that like it's not implementing the join, and it's not representing the join, because the join that we're trying to deal with is the one at the root here, right? It's just saying you're going to get data from me that you can then that'll be the join of A1, A2, A3, and it'll be sorted. But I don't know how physically I'm going to actually implement those two steps. Yep. So again, the enforcers, there's placeholders, right? Because like you wouldn't actually implement it in your system. What does that mean to say check the data is actually sorted? Right? That would be wasteful. You should just sort it, or make sure that the operator that's going to give you the data is sorted. All right, so we're going to do depth first search. So say we're going to follow down here to now the cert merge join, right? So what we got to figure out is, okay, well, I'm doing a cert merge join on some join result of A1, A2, and whatever their in result, that's going to join with A3. Okay, well, how did I get those two inputs into my sort merge join operator, right? I would then connect it to the logical operators here, right? So you have a join with artists and appears. That's being fed in for the join A1, A2. A1, A2 are just aliases. And then here's the scan on the logical scan, our access method on album, and that's the other side of the join. Again, these are logical operators. I didn't say how I actually generated those, right? I'm just saying data's coming in, and it's going to provide this logical construct or logical result. So I do the same thing. Now I'm doing depth first search. I jump down to artists and appears. And again, now I need to do the same thing that I did before, where I apply a implementation rule that converts the join of artists and appears into different combinations I could have, either a hash join on or the merge join, right? I could also apply a logical transformation to do convert it to appears joins with artists, right? And then you have a bunch more logical operators going that way. But keep it simple. Okay, so now again, I have my two choices. I do hash join or merge join, right? So I scan down here. It's the same thing. I'm now going to connect to saying I have a physical operator that's doing a hash join on A1, A2. Well, that's artists and appears. There's a connection now between the logical operator saying you're going to get the data that you want from these two tables. I'm not telling you how I'm actually going to access them, but here's where to go get them in the query plan. So then now I do the same thing. Traverse down here to artists, apply the implementation rule to convert the different access method choices I have. I can either do a sequential scan or a next scan. I go down to the first one here, right? Get a cost, come down here, get index scan. Now I get a cost. And if I wanted to at this point, I could then make a decision which of these two are going to be the best choice for me at this point in my query plan. So I don't have the full cost now of this query, but at least now within this branch, I'm going cert merge join to the hash join to the sequential scan or index scan. I know what the cost is for that side of the query tree. I bounce back up to artist, bounce with a hash join. Now I need to go to the other side where I'm joining A2, right? And maybe I misspoke. We don't have the cost of this because we got to go down here and figure out how we're going to access the peers. And say it only has one option, sequential scan. That has a cost. Now as we come back here, now we can be able to cost the hash join in its entirety because we know how we're going to access artists. We know how we're going to access appears. So now we have the cumulative cost for this point in the query plan, everything below. And then now we got to go back up to the logical operator for the join, go down to the merge join, do the same thing. But now for this point here, the merge join algorithm is accessing the same tables as obviously the hash join one, right? Because they're both derived from the same logical operator. So at this point here, I don't need to go down to the query plan, or sorry, the lower part of the tree, because I already know what's going to be the lowest cost to access artists and the lowest cost to access appears. And so I can just skip that traversal entirely. I would find the cost in the hash table, the lookup table that they're maintaining, so I could reuse it. So then now I bop back up to the root of the tree, and now I go down the other side and I'll start looking at the enforcer, right? So again, the enforcer is just a way to have a placeholder in the query plan and say, I'll provide you the result that you want, that's defined in the logical operator that I'm connected to, and I'll guarantee that's going to make sure that it's going to have the properties that you care about. So in this case here, we're going to care about the sort order. So okay, well, the first thing I could do to make sure that the data is in the order that you want is I'll do a quick sort based on the artist ID, a1.id. And then now I traverse down to this and say, okay, well, I still need to do the join on A1 and A2, A3. So I could generate now a hash join for this, similar to the ones we had over here, right? But now at this point here, if I go to, I may not even need to go down and look at it, because I would know that the lowest cost I've seen so far to join A1 and A2 as defined by the sort merge join, that's going to have some cost, which is the cumulative cost of all the physical operators that I chose down below. So as I'm traversing this tree, I know I'm trying to satisfy the join on A1, A2. So if I get to this point, I compute that the cost of this hash join is, without even defining what the cost of the access methods on A1, A2, and A3 are. Meaning I'm not saying how I'm actually going to get the data to do the hash join. But if I recognize to compute this hash join, in this case here, I can reuse the results from, well, that one got pruned earlier. But at this point here, I don't need to even do expansion down below, because I would say if this cost of this quicksort is so expensive that it's way more than whatever the sort merge is, then I can just prune this branch entirely. And I don't need to traverse down and even examine it. Yes?
So the costs here are added together, but in Exodus they are multiplied together using a cost factor. How is that reasonable? How is Exodus, that method reasonable?
So this question is, in this one, the total cost of the query plan is the summation of some path up to the root, right, of that branch. In Exodus, you had this total cost, which is the sum of everything below you, sort of similar. But then I threw in this other factor in, right? That was figure that more as a hint to saying, like, if I apply this transformation rule, am I going to get better, yes or no? So it's like, and then they had a way to say, to adjust how pronounced or how large that weight affected things.
So the Exodus cost model, does it look like something, some terms are added together, but some of the added terms are multiplied by a factor?
The question is, in Exodus, is the total cost computed from adding things together, but then sometimes you adjust things with that factor? Yes. That's how they're going to do prioritization. In Volcano, they're not going to have that. Cascades will, yes.
So after that enforcer, is the sort merge join A1, A2, like A1 join A2, and then A3 is also an optional path, but we already visited that, so.
Yeah, he's correct. So what he said was, after this enforcer, I showed one path going down with the quick sort file of the hash join. But is it the case that this thing would also satisfy that? Yes, I'm just not showing the edge. And then because it's in the lookup table, I would do this, say, okay, well, I need to make sure that whatever I'm getting out is going to guarantee my data is going to be sorted. Oh, I have a transformation rule or implementation rule that'll convert that enforcer to also then be the sort merge join. But then I look on my lookup table and I see that I already done it, and I don't need to repeat that search.
It isn't obvious to me why you can't do top-down with a breadth-first search approach. And is there a reason you wouldn't want to do that at all?
His question is, there's no reason to do depth-first search here. Could you also do a breadth-first search?
It would be hard to get the costs. I think.
Yeah, the problem is you'd be sort of going wide,
Right.
and then you have no way. It's basically what X was doing. It was going wide, and then now you have a bunch of things at the higher plane of the tree that you've expanded out. So now that's blown up your lookup table. Again, it's the 1990s. It didn't have a lot of RAM, but then at that point I can't prune anything because I don't have costs. I can prune things based on properties, but I got to get to the bottom to figure out what that, what the lowest physical operator is to then get the cumulative cost up the branch. Then I can start doing the branch bound pruning.
I see. And so the conversation we had in like 2 lectures ago about mixing bottom up and top down, what you really meant was you can do the breadth first search approach of expanding everything with join orders, but in reality do top down so you can prune stuff.
No, I think the comment that Gertz Graffi made about like,
Yes.
that's more like I meant that like you could do a that you could not do all possible combinations of the join order, and then do that as a separate phase through the hypergraph stuff from the Germans.
I see.
It's kind of weird. I haven't thought through entirely how to do that yet, but I think that's the way you would do that. Like you could just say, I'm not going to expand out. I'm not going to apply cumulativity rules to reorder things.
Okay.
Now that sort of violates what the in the Volcano paper talks about, or I think Starburst talks about as well, is like that you want to be able to pick the access method in conjunction with the sort algorithm you're using.
Right.
And so do you not do this step down below? I think you would have to. Yeah, I haven't thought through that comment. So again, the background is the guy that invented this, all Volcano stuff, when he won this big award at SIGMOD in 2018, in his speech he was like, yeah, Cascades is actually kind of complicated. If I had to do it all over again, I would do Cascades first, then do the German's join algorithm, join search algorithm we'll cover later. Even though Gertz is he's also German too. So he didn't obviously refer to it as the German algorithm. You know what I mean? Yeah, we can sort that out further later on. All right. So this is the fourth lecture we had this semester, and we haven't even looked at one graph. This paper has a graph we actually can use. Right, because you think about it, like, we're going to see this over and over again in all the papers we read the entire semester. They're not going to compare against other query optimizers. I mean, certainly in the 80s, in the 90s, there wasn't a bunch of these, off-the-shelf query optimizers you could use, and it doesn't make sense to benchmark the entire system. Like, take a query, run on some version of Postgres, run on some version of Oracle back in the 1990s, because those are completely different code bases. The engines would be completely different, and it's kind of tricky to then be able to compare like the query plans for telling different environments. So you're not going to see a lot of different comparisons between these query optimizers. You'll see papers where they from the Germans, they'll compare against their previous incarnations or their previous implementations of algorithms within their own systems. And then one where they're going to look at the cardinality estimates of a bunch of different database systems and show how off they actually are. And in that one, again, you can do that, actually compare against them. And then when we do UDIF interlining, I'm jumping way ahead, we also looked at different database systems to see how good their optimizers are. But you're usually not going to see graphs like this. And there isn't a standard benchmark other than the joint order benchmark. But that didn't exist in the 90s. There really isn't a standard benchmark to say how good my query optimizer is, because there's just so many factors involved. So they're going to compare against the Exodus query optimizer and the new one they built in Volcano. They're running this on this old Sun machine back in the 1990s, and so they're going to basically do fuzzing of looking at a number of different tables they want to join together in the query, and they'll have 50 queries for sort of each category here. And so they're going to measure how long does it take for the query optimizer to produce whatever it thinks is the optimal plan for each given query. And you can see that when the number of input relations is very small, right, even on this old machine, it can produce a good joiner in less than a second, right? But it's when you go from 2 to 3, Exodus balloons up because again, it's because it has to represent the same logical operator over and over again in that mesh table. It's just, the search becomes untenable, right? And in the case of in Volcano, they're scaling roughly linearly to the number of input relations here, right? Even though it's log scale here. All right. This is not a good graph because they mention in the paper that in the case of Exodus, the behavior was really, really volatile. Some of the queries completely timed out. So this is just reporting the runtime of the queries that actually did complete. So they don't say what percentage of the queries fail, right? Is it 1 out of 50 or 49 out of 50? It doesn't say, right? So it's just, but this is the first measurement we've seen of like how good a query optimizer actually is, right? Again, the big jump here is because of that mesh table that they reanalyze, subplans over and over again because they can't keep track of, I've already seen this thing before, whereas a Volcano that they can't. So they dunk on their own previous papers. That's good work. I like that. But then they also take a shot at Starburst, and these are qualitative arguments that they're going to make. And to me, some of these make sense to me. They resonate. But again, as I said, the lines kind of get blurry when we start looking at Cascade, especially in Microsoft. That like they're going to have what you could call is like the rewrite phase, where you're applying rules without a cost model to get to the query in a form that you actually need. But at least in case of Cascades, it's just 2 algebras that you have this, the logical algebra and then the logical operator algebra and then the physical operator algebra. Whereas in Starburst, you had this query graph model, then you converted that to this star lollipop thing that was completely different. Whereas in Cascades and Volcano, it's all within the context of just those 2 forms, 2 types of expressions. So they're going to argue that the way Starburst implemented their rewriting of the rules for when they do the cost-based search is too convoluted because you have this hierarchy of that the logical operators can get converted into combinations of more logical operators than the physical operators, and that if someone wanted to come along and introduce new operators or a new data model, they would have to figure out how to make that fit into the things that already existed in Starburst. So what they're referring to is basically this diagram that I showed before, right? That you have some kind of access route, and then you have all of these, sort of traversing down into the access methods. So if you had to add maybe like a new index type, maybe that's too obvious how to make that work here, but like if you had to implement something that maybe in between the index scan and something else you wanted to do, they argue that to actually implement that would be quite difficult. Of course, we haven't seen the Starburst source code or in DB2, so we don't know whether that's true or not. And so they claim that if you just have a single level of rules, again, the transformation rules and the implementation rules, then that's way easier for someone to come along and reason about how to add the things that they need to extend the query optimizer. And then we'll see this in the case of Microsoft, you still can do what Starburst does to do the rewrites without cost model, but just giving those things a higher priority and running those in the beginning, and then change the phase of the system or the optimizer to then consider other rules. And that's what Microsoft does. This is just a summarization of what I already said before, right? Yeah, you want the idea that you want to compile your rules. That's a good idea if you want to create optimizer. And then you can achieve better sensibility through compilation because now you don't have to worry about this interpretation and making things slow. And although they don't explicitly call it memoization, we'll see this more in Cascades, but the idea of keeping track of what rules you applied before and what their cost is, and that allows you to do the pruning necessary to avoid unnecessary computations. And again, the big challenge they're going to face is that they have to expand everything before they actually do the search, and that's going to be a problem that Cascades will fix. All right, so this is basically what I just said. If we expand all the equivalent classes ahead of time, that's going to suck. In Exodus, we saw where they were trying to learn on past behavior to adjust the search process, the priorities, to prioritize the transformations that you think are going to have a bigger win. And then if it doesn't work out, then they're given lower priorities, so you don't apply them again. Volcano doesn't do this, but they have this little blurb here in the paper where they talk about that it would be kind of nice to not have to reinitialize the hash table, the lookup table, every single time for every single query. And that ideally what you want to be able to do is maintain some state about the transformations that you've applied for a query plan from one invocation of that query to the next, so that you can short circuit that full traversal to the bottom and figure things out. You just look up in the lookup table and you find a good query plan ahead of time. And as I said, it's very complicated to do this, especially if your data is evolving. Right? The papers you're reading, they're talking about, oh, the tables have 1,000 tuples. Like, that's obviously nothing these days. But back then, that was a lot. And so they say we are considering research into longer-lived partial results in the future. Volcano never did that. Cascades never did that. I don't think Microsoft will do this, and we'll read a paper on plan stitching later on. So there's seeds being planted here for things that are to come in papers that were written after you guys were born. All right. But back in the 90s, they were just saying, hey, it'd be nice to do this. Yes?
So another advantage you mentioned was it wasn't easy to modify predicates. What does this mean? You made. I don't remember when I read this. I don't think I meant my predicates. I meant the transformation rules, like that you had to, since it was compiled, you had to make changes, recompile the whole thing, and inject it back in, right? Where they call out Postgres. Postgres, you can augment the optimizer by putting in rules at runtime without having to recompile everything. Starburst claimed the same thing as well. So it's actually not easy to modify the
behavior of the system. Yes, that's the typo. Thank you. All right, so next class is going to be about cascades. There'll be no reading synopsis due. I'd rather you have spend your time reading the chapter. I'm trying to think what's the level. I mean, they're going to call it explicit functions that they have for the search algorithm. But now that you have the context of understanding what Exodus and Volcano does, you'll just be able to see, start to make more sense of like what cascades is actually trying to do for you. So again, don't do the synopsis. I'd rather you spend time reading it and understanding it more clearly. Okay?
Look good with brown. Matter of fact, hold the cup. This is like that wood grain type of shit. Shout out to Blockhouse, my dogs. Catch one, Big Al, Mike Stroke, Gumby, all that matters. I'm not the one who be amping up the weak ass rhymes. If you spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as the thug from the gun. Shit, some niggas claiming never rapping is sudden. Don't push the button, yes you motherfuckers are frontin'.